single network. But when you have multiple devices that must share a single medium, then you have to choose how to control them, the traffic control technique. So they can be categorized into 3 different categories. First one is random access. Second one, controlled access. Third one, channelization. The first one, so these abbreviations, acronyms of in the red, well, even the first one, ALOA, is an acronym. Those are the actual name of the algorithm or technique. ALOA, you don't really need to remember that. That's more kind of experimental protocol, so we don't use them. But you have CSMA-CD, CSMA-CA. You have to remember those, both of them, because they are very, very widely used. Can anyone guess where we use them? CSMA-CD, CSMA-CA. Have you heard those terms ever before? Right? That's how you have been insulated from what's going on under the hood. No, actually, we use them in data communication. Where? In two most popular data link layer protocols. What are those? What are the 2 most popular data link layer protocols? What do you use now? Huh? So what kind of data link layer technology we use for internet connection? In the data link layer. Ethernet? Yeah? Ethernet. We all use Ethernet here, right? In front of you. How about the other one? What's second most popular? Or maybe that's most popular for end users? Wireless LAN, right? So CSMA-CD is how you share this medium with your Ethernet. And CSMA-CA is how you share the radio signals that we use with the access points. We have cell phones that are connecting the access point. How many of you are using cell phones with Wi-Fi connection? We have only one access point in this area, right? So we all share the same medium, and we use CSMA-CA to make sure we don't fight, we don't have to throw fists to each other to just use the signal. So remember those terms, okay? So once you take this course, at least you have to understand. When someone says that, you should be able to tell, hey, that's for Ethernet, that's for Wi-Fi. So at least we showed some geeky flavor in this course. And then controlled access is a technique when you still have a single medium that only one device can use. You can either use reservation, polling, or token passing technique. How about random access? That's, as the name says, it's random access. It's wild, wild west. Anyone can jump in to transmit something whenever they want to transmit something. If something happens, take care of the mess and then try it again. Controlled access is pretty well-ordered, predetermined process that you have to follow all the rules, so there will be no big mess in controlled access. How about channelization? If your medium is broadband medium, like a high quality copper coaxial cable, or fiber optic cables, or the air, that we have only one atmosphere anyway. We use FDMA, TDMA, or CDMA. Hey, have we learned FDMA or TDMA? Or we learned something similar? Do the acronyms sound familiar? FDMA, TDMA.
Yeah, we learned those without the A.
Without the A, right?
Correct.
So what does FDM?
Frequency division.
Frequency division, multiplexing, right? TDMA, time division, multiplexing. Here, it's multiple access instead of multiplexing. So multiplexing was happening, multiplexing is a physical layer technique. So the individual source and destination device are dumb. They don't know how to share. So there should be a multiplexer and demultiplexer that do something, so modulate the signals, and then put them together to share the trunk medium. And then there's another device on the other end, that's a demultiplexer, split the individual individual signals and put them back to the individual devices. Here, we are talking about Datalink layer. That's inside of the device. So these are for smarter device who should understand what frequency they should use to modulate their own signal. There's no third party that does that for the actual signal transmitters. But you are the one that have to modulate using frequency or share the time, understanding the whole context. But the actual results are the same. You share the medium. Whether you do it in the Datalink layer or ask something else, like a multiplexer, do it outside of your device in the physical layer. CDMA is another technique that for digital medium, digital devices use codes called chip code and use mathematical calculation instead of frequency or time or physical characteristics of the medium. We use the number theory to kind of put all the ones and zeros together and still allow the receiver to extract original ones and zeros using calculation. And have you heard the term CDMA somewhere? Sprint CDMA. So that's like a third generation mobile communication technique, right? So those handsets, not these days. These days we use CDMA and some other techniques combined together, but back there it's between TDMA or CDMA. So TDMA was used in Europe. GSM used kind of TDMA version, and Sprint used the CDMA, and different handsets use different chip codes to kind of plug in their ID in their signals when everyone shoot out their signals and share the single medium. GSM systems use time sharing, like a TDM. They just know which time slot they should use, so that's TDMA. So if you're using random access protocol, it's like this. Dear drivers, you are driving cars with other fellow drivers. So dear drivers, follow the guidelines. So you have a minimal set of guidelines that you have to follow. Individual drivers must follow. But enter the road at your own risk, and you will probably have an accident. Good luck. If you are using controlled access, for example, like a token passing, it's like you have multiple cars that must drive, but only when you have a tag. You must have a tag to drive the car, but when you have multiple cars, you have only one tag. What can you do? Pass it around, right? Only the car that has the tag can drive, and as soon as you come back, pass the tag to the next car, so the next car can drive. Channelization is like when you have multiple wide, high capacity road system. You divide them into smaller lanes, so multiple signals can travel together at the same time. So the MA stands for multiple access, and in random access, multiple devices are connected to medium, and anyone can shoot out their transmission anytime they need to transmit anything. So collision is very likely. What if you pay attention to the road and you don't see any cars coming, you don't hear any engine sound? Do you still have an accident? Yes, because some car can drive very fast. Even if that car is out of your sight and you cannot hear any noise, there can be still a car that's coming, and as soon as you pull up your car off your driveway, you can hit your car and create an accident. So that shows that signal can travel through this medium, and although the time difference between the signal actually transmitted and heard by another device can be very short, we are talking about very high-end device transmitters. They can transmit at very high speed, so that much of time, that little bit of time can still be enough for a device to transmit the data and create a collision. What happens when you transmit something when someone else is transmitting as well? Here we are talking about baseband transmission. What's baseband transmission? As opposed to broadband transmission.
Just one channel.
Only one signal can travel through the channel. Why?
One frequency.
Because you have to have that frequency to use that communication. What frequency is that? Zero frequency. So digital signal must use zero frequency signals, and that means you have to have only one signal at any given moment traveling through the medium, right? What if more than one signal is transmitted through the same medium? There will be collision. So let's say you have 5 plus 5 and 0 volt signal levels, one for 0, one for 1. And the other device will do the exact same thing. And when there are two signals coming in, plus 5, what happened? They hit, and the total signal level will be plus 10, right? That's illegal in the protocol. So there will be collision. You have plus 5, and the other guy has 0, collide, what happened? No change. But can you tell whether that 5 plus 5 volt is the original 5 volt, or there was a collision and there was somewhere between 2.5 and 2.5? Well, can you tell whether that's from single source or two sources collide? Although there's still 5 volt, it can be 5 volt from 1, or it can be 5 volt from 2, and there's actually hidden volt, 0 volt signal from the second source. So you cannot extract the original signal when there's any collision between more than one digital device. But there will be ones and zeros. So plus 5, 10 volt will happen sometimes. But so if you sense at some point 10 volt or anything above 5 volt, then you should limit in normal situation. You can guess there was a collision. And CSMACD, that stands for collision detection. Carrier sense multiple access with collision detection. So CSMA is carrier sense multiple access. CD is collision detection. Actually use that collision signal to identify possible signal conflict. So all the devices on the computer, on the network, will constantly listen to the medium and sense the signals. Okay? There can be a time period where absolutely no voltage can be sensed. That means no one is using it. And there can be some plus here and there, that means someone is using it. If you see anything above that, you can say, hey, there's a collision. And if you just transmit it, you can guess, hey, because of the collision, my signal might have been like crashed somewhere and could not be delivered to the final destination. So I got to retransmit. So CSMA-CD follow this flow chart. So transmit whenever you have something to transmit. See if there is any collision you could hear. If there was a collision noise, then wait and retransmit. Okay? What if there's another collision? Wait and retransmit. What if there's another collision? Wait and retransmit. Just repeat to the whatever number limit, and after that many trial, and if you still could not transmit it successfully, you just give up and send out, display some error message or something. So that's basic approach in CSMA-CD. Accident happens, and CSMA-CD focus on the steps to take care of the mess and make the participating device retransmit as soon as possible. It's very chaotic. It may be good if you have only few devices connected to a single network. But as you attach additional device, the chance of getting a collision goes higher. And as the collision goes higher, you have to wait more. Then there will be more device that needs to transmit. So the collision rate or possibility will just skyrocket, exponentially increase. So there was a big problem in the early days of Ethernet because Ethernet used CSMA-CD. So this is how it goes in a nutshell, although the actual flow chart can be a little more complicated, but you don't have to remember all these steps. This is actual algorithm that you will use to follow if you are developing Ethernet protocol. You don't develop Ethernet protocol, but implement an Ethernet protocol for a network device, network card or switch that your company is developing. Oh, no, not this one. This is CA. Sorry about that. That should be CD somewhere.
Is that in one of our PowerPoints? That graph you just showed?
Oh yeah, this one. Sorry about that. So there are some specific rules that you need to follow, but that's the general idea. Just transmit whenever you have something to transmit. If there's a collision, step back, retransmit as soon as you are ready. No, this is CA again. Where's CD? Maybe I didn't put it because you don't really need to remember the exact steps, but this rough idea of how it flows is should be enough. So if that was CSMA-CD, what's CSMA-CA? So the first part is the same. Carrier sense, multiple access. That means everyone listen to the carrier, the medium, where multiple computers or devices are connected to the same network. And how to maintain the sanity between the devices when we need to compete to transmit? It's CA, collision avoidance, as opposed to collision detection. So CD focus more on taking care of the mess when you assume that there should be collisions. Here, if possible, let's just avoid the collision at all. Okay? So it's a little bit more complicated. Basically, you make individual device to wait for different time amount and do some precaution steps to avoid the possibility of causing an error. There can be some collisions, but the chance of getting a collision will be lower than CSMA-CD. And where do you use this? Wi-Fi, yes. One big problem of using CSMA-CD is you cannot apply that in wireless device, wireless network environment. To use CSMA-CD, collision detection, like Ethernet, you should be able to listen and hear all the collision sounds, right? because if there's no collision, you assume that your transmission was successful. In Wi-Fi world, you may have access point in the middle, and mobile device on each side, okay? And the signal strength for individual device can be just enough to cover its communication partner, right? So access point can cover wider range, covering both mobile devices, okay? Your cell phones and laptops. But device A can communicate with access point, but not B. It's out of the range, right? So if this guy transmits signal, this guy transmits signal at the same time, there may be some collision here. This guy may hear that collision noise, but this guy cannot because that's too soft for device A to sense. It's too far away. So unlike guided medium, the unguided wireless communication has some different approach to make sure that that kind of thing does not happen, so it does not have to rely on sensing the collision sound. What are those? So as I said, you make individual device to wait for different amount of time before they actually transmit, even if they hear that no one is using the medium. So we all have something to transmit, and we all listen to the medium. It's quiet. Okay? Instead of allowing anyone can transmit at the same time, each device has a number card. And whatever the number is you have to wait for that many seconds. If I have 1, the number 1 in my card, you have 10, who transmit first? Me. Right? So I can transmit, and by the time I transmit, you hear that noise coming from my transmission. Also, in addition to that, you transmit special packet, control packet called RTS. RTS, that stands for request to send. You just don't transmit your data, you send RTS packet first. And your communication partner, if that's an access point, have to return with CTS, clear to send. If you don't get clear to send, you don't transmit. Right? So that way, only one device will be allowed to transmit. So the chance of getting a collision will be very low. And also, after you transmit, you wait for acknowledgement. So in Ethernet, if you don't hear collision sound, you just assume that your transmission was successful. Okay? You don't retransmit. If you didn't hear any bad news, you don't retransmit. Here, if you don't get acknowledgement from your communication partner, you assume that there was a problem and you retransmit. That's how you don't rely on sensing the crashing sound, but have explicit control message that says you are ready to transmit, you are allowed to transmit, and then here's the receipt. I got your message, so you don't have to retransmit. If you don't get it, you retransmit automatically. This is a contention window. It's a concept where you are waiting. Okay, IFS interframe space is the time amount that you have to wait. So you wait there. After no one is transmitting, you sense that no one is using that medium, you wait for IFS. And then you wait again, and that's contention window where individual device is assigned to different slot. If I'm there, I can transmit something. You raise your hand. Hey, I have something to transmit. If your slot is here, you cannot raise your hand because I already raised my hand here. That's how you prioritize different devices randomly or dynamically. And then only if you could raise your hand, then you can move on to the next step to transmit your data. Again, you send out RTS, request to send, I have something to transmit, and then the communication partner should send a clear to send message back. And by listening to clear to send, the other device can sense that, hey, device B is occupied now, and the channel is being occupied now, so we should not try to transmit RTS again. No, sorry, RTS again. Already a new transmission is going on. And in the CTS control message, it also has a value called NAV, network allocation vector. That's again time amount, saying, hey, device A is about to transmit something, and that's gonna roughly take 5 seconds. So don't even bother to listen. Come back after 5 seconds. So that during that amount of time, C and D assure that we should not use the device, should not use the network, or try to share the medium because it's being used. And at the end, you have to transmit acknowledgement to the sender, and without that, the sender will retransmit. Any question for the random access approach? Controlled access can be reservation, polling, or token passing. Reservation is like you have preset time slots that are assigned to different devices. So you can transmit your stuff only during that time period or following that order. Whereas polling is that's for usually you have 2 different types of device. One is the primary or master, or the others are secondary or slaves. Okay? It's like a old approach when you had this mainframe or mini computer with terminals and auxiliary devices like printers. The primary can only transmit stuff without permission. So if primary has something to transmit, just send a selection frame to the receiver and say, I'm gonna send some data to you. And then the secondary will usually, unless there's some problem, will come back with acknowledgement, yes sir. And then you transmit, and then acknowledge. If it has something to say A to A, then send the selection to A and then say, get this, yes sir. If the secondary or slave needs to send something, it cannot transmit just like that. It has to wait until the primary asks, do you have something to say? So send the poll frame to A, and if A device does not have anything to say, no sir, I have nothing to transmit. Then primary go to the second one and say, do you have anything to say? If it does, then say yes, and send the, no, you don't have to say yes, but just send the data, and then the primary will acknowledge. So that way, collision will be prevented because only one device who can transmit is either the primary or the one that primary pointed out. Okay. Token passing is when you have multiple devices connected in different topology. It doesn't have to be a ring. It can be a bus or star, but logically there's an order. So individual device has the order. Then order will be like the numbers on the clock dial. So from 12, 1, 2, 3, 4, 5, all the way back to 11. And there's a special frame or packet called token. Okay, that's not a data frame, but it has a special signature, ones and zeros on there. And only the device that has that token can transmit. And all the transmission will be sent to the same direction, clockwise or counterclockwise. Once you decide, you follow that all the time. So if device A does not have anything to transmit but has a token, that device will pass the token to the next device. And the next device to the next device to the next. Until the device that has something to transmit receive the token. Then it can transmit. And once the transmission is over, the token can be passed to the next one. Channelization, almost exactly same as the multiplexing technique, but the selection of the frequency in this case, if you are using frequency division multiplexing, what should be the carrier signal? What's the frequency of your carrier signal is predetermined, and the data link layer module inside of the individual device already knows what frequency they should use. Like the first generation FDMA mobile phones. So the first generation cell phones use FDMA, and whenever they are connected to a station, they are assigned to a carrier signal. So, hey, you use 10 megahertz, that's yours. Your friend uses 11 megahertz. So they use different carrier signal frequency to modulate their signal within the device itself and then transmit. So once they are all transmitted, they are combined in the air, but you don't need multiplexer or demultiplexer because individual device already knows and modulates their signal within the device itself. No mux. TDMA, as I said, GSM, the third generation cell phone use GSM, TDMA or CDMA. So TDMA individual device has this time slot already known to themselves. So they use that time slot only to transmit their data. CDMA again said use a chip code. So when you first power on your cell phone and it connects the station, you are given a chip code that's unique code, ones and zeros, and every time you transmit 1 or 0 in digital bit, you multiply them with chip code. If you have, for example, if you have 4-digit chip code, for example, just because chip code can be very long, every bit you transmit will be multiplied by 4 because you multiply individual bits in your 4-bit long chip code with the original bit that you want to transmit, 0 or 1. So the data amount actually increase, but once you transmit in the air, you don't have to worry about anything. You don't have to split your frequency, or you don't have to share the time with other devices. You can use the whole spectrum of your frequency given to that service, in which case there's a CDMA cell phone service. They are just jumbled together, seemingly they are encrypted, but the receiver, the cell phone station, knows all the chip code and use that chip code to multiply and extract the original bits. That's how we share the single medium with multiple devices for your Sprint customer. Any question? So that was about the framing part, the data link control and the multiplex control part within the data link layer. What are the functions that has to be done in the data link layer? In this slide app, we talk about the details of Ethernet and wireless LAN. Those are two the most widely used data link layer protocols in consumer network environment, and also talk about the devices used to connect multiple LANs or multiple networks. So we talked about standardization of protocols. And all the internet protocols should be standardized by IETF. It's a kind of sub-organization of internet society. But we are talking about data link layer, which is the infrastructure. Okay, infrastructure, what kind of infrastructure, network infrastructure you have, you should not determine whether you can use the internet or not. Okay? So it's kind of independent from the internet itself. And the standard was set mostly by IEEE. That's the biggest organization of engineers. And in the term that we used in the previous slide deck was a data link layer, data link control, which maps to logical link control. That's where you have framing and flow control happen. MAC is still MAC, media access control, or multiple access control. Those are sub-layers that we saw earlier. So if we are talking about the Ethernet, the logical link control is where you use the rules to set the structure of the frame. So how long a frame can be. What's the first part? Header. What are the headers, the subfields inside of a header? How long the data field can be. And what's the trailer? Those are determined here. If there's any error control, done here. This is the lower half of the data link layer where you specify what kind of connection or topology it has to be done. So you have Ethernet MAC, token ring MAC, token bus MAC, and there are some others that are kind of dead long time ago. So we use mostly Ethernet MAC these days. They use bus topology. And then within that Ethernet MAC, you can choose multiple standards in the physical layer depending on how fast you can transmit data, transform the data and generate the signal. How many lines do you need to transmit data, or what kind of medium do you need? Fiber optic, is that multi-mode or single mode? How long can that transmit without regeneration of the signal? So Ethernet spans across these two layers, physical and data link layer together, but there can be multiple components that you can just mix and match. And the top part, LLC part, logical link control or data link control, they never changed since the very beginning of the Ethernet. And this is another thing that you need to remember, at least, if you want to say, I took a networking course, IEEE 802.3 or 802.3. All Ethernet related protocols start with that, IEEE 802.3. And you can have some additional lowercase alphabet after that, but that's different flavors of Ethernet standards. So 802.3 or 802.3, basically you can use that term interchangeably with Ethernet. They include both data link layer and physical layer. As you can see, in the physical layer, you have standard Ethernet, fast Ethernet, gigabit Ethernet, 10 gig Ethernet, and you have more, although they are not very popular these days. And this is the frame structure that never changed in the past 4 decades. So you have preamble, and also this gray part is still not a part of the official frame structure. The very first field in the header is destination address, and then source address. Of course, they are MAC addresses, right? And then you have length or type field. So you have only 3 fields in the header. Not very complicated. only 3 fields in the header, and then data field, and then CLC, that's what? Error correction, not error correction, error checking part. So that's trailer. Only a couple of different flavors or additions to the original Ethernet frame is two functionalities that are widely used these days. These days we use VLAN a lot. We'll talk about what VLAN is soon in a few slides. But to maintain the information about VLANs, the membership of your LAN environment, there is an additional standard that allows to plug in some additional bits inside of the header of original frame. So in that case, your frame length will increase by a few bytes. Another thing is, there's something called the jumbo frame. The jumbo frame was kind of proprietary technique that was used to increase the size of the data field, because if you think about the structure, the biggest size that you can have in your data field in your Ethernet frame is 1500 bytes. Why? Because this was developed 40 years ago, and that was the beginning of the networking, and the network reliability was bad. You could have noise, you could have lost frames and things. Whenever you have problems, you may need to retransmit. So it's like you gotta your friend asks for a song, and so you just talk over the phone to read through the song from the beginning to the end, and that's a very long song. And at the end, your friend said, sorry, I kind of lost in the beginning. Can you say it again? What a waste. So if you chop that into small pieces, then you can have faster feedback, and that in general, statistically, you can reduce the waste of retransmission time. So they came up intentionally with the small frame, which gives you very inefficient structure where you have 662, the 14 bytes of header per every 1500 bytes. So as the reliability of the network became better and better, and speed goes higher, they wanted to make this data field bigger, but there's no standard to make a bigger frame. LAC part is always the same for backward compatibility. So there are some proprietary vendors, protocols that bigger vendors like Cisco or the Ethernet network card manufacturers came up to use illegally long data field for the same header length and same trailer length. That's what you call jumbo frame. If one device uses jumbo frame, the others cannot handle a jumbo frame, there will be no communication. So that was very limited use usually within a single data center. But these days, everyone wants to use jumbo frame. 1500 bytes is too small. So one of those many jumbo frame proprietary protocols became obsolete, but one of them are chosen to be a standard. And these days, even if you buy your device from different vendors, like you have Cisco switch and Avaya router and Intel network card, they all use the same jumbo frame standard, so they can use this huge 9,000 byte long data field frame without causing problems. So those are the only two exceptions. The 40-year-old frame is still being used, but that can be a little longer if you have VLAN tagging information, or within a single network, you can choose to use jumbo frame if all your devices, network device, can support jumbo frames. This is also another very important term, MTU, maximum transmission unit. Maximum transmission unit refers to the largest size of your message that can fit in the cargo area of your frame. The frame is actually the one that actually transmits, goes back and forth the medium, right? So all your message should be small enough to fit in a single frame data field. So before you actually, your IP or even TCP build their message, they may want to check with their Datalink layer module and ask, hey, what's your MTU? If that's 1500, you better make your frame or your TCP message or IP message smaller than that so they can be encapsulated without causing problems. So depending on the generation and the specific physical layer standards, some used 2 pairs of UTP cable, the Cat5, Cat6 cables. Some used 4, some used 5 optic cables, some used copper coaxial cable, and depending on which one you choose, the limitation and performance all differ. So these are, they are not exclusive, they are not exhaustive. They are more physical layer standards, but these were more popular choice in the market back in the 90s. And then I already showed that a couple of weeks ago. Fast Ethernet start to use some fiber. So FX, here F stands for fiber. By the way, if you look at the Ethernet physical layer standards, they all start with a number. Okay? Either 10, 100, 1000, or 10G. They refer to the speed, transmission speed or bit rate of the standard. So here you can see that's fast Ethernet because they all have 100 in the beginning, meaning 100 BPS. The original has 10 in the beginning. All of them have base, right? That means they all use baseband transmission, digital transmission, right? And then the next part after dash usually refers to some kind of specification of your physical layer medium type. So if you see a T, they are usually the copper cable, UTP cable. If you see an F, that's usually a fiber. These days, when you have gigabit Ethernet, you have more fiber standard in the physical layer than copper. If you use copper, you may want to use this standard that use STP instead of UTP. U stands for unshielded. S stands for shielded. So that can provide higher quality and better noise insulation characteristics for higher speed transmission. For 10 gig, mostly fiber, and here S, L, E stands for short wavelength or short range, L, long range, and extended range. And depending on which implementation standard you want to use, you will have to choose the different fiber optic cables. So SR use multi-mode. Remember multi-mode and multi-mode versus single mode? Multi-mode let the light signal bounce off the wall many times, so the received signal can be dirty. It can be fuzzy. whereas single mode is the light signal follows through the very center of the core, so the received signal is cleaner, so they can go farther. You cannot just receive a dirty signal and use it. That means if we get dirty signal faster than single mode, then you have to listen to the signal faster, earlier. So the range is shorter. So typically within 300 meters. So on a single floor or single office or single data center, SR is good standard. Fiber optic cable is cheaper. But if we are looking at the long range connections, like across the big campus, like Stillwater, or between different areas of the cities, or across the city, or across states, then you have to use EW support up to 40K. And these are the standard minimum. If you use good quality fiber optic cable and transceivers, that can be even longer than that, but there's no guarantee. This 10G base X4 use 4 threads of fiber optic cables and use WDM. What's WDM? Wavelength division multiplexing, right? So that's how you modulate different portion of the signals using different colors of your light or frequency of the light. Combine them and send them over 4 fibers, either to increase the speed or increase the range. In terms of the devices that we can use, I said if we increase the number of devices that are connected to a single network, the throughput can go plunge, and no one can actually transmit anything if the collision happens so often. So having so many devices connected to a single segment of a network is a bad idea. So you want to divide them into multiple domains, and these domains are the collision domains. If this medium, this section of the medium is shared by 3 computers, and if any 2 of the 3 transmit at the same time, there will be collision, right? But that collision does not have to be heard by the other part, because you can put a device called bridge or switch that will selectively forward the frame to other part of the network. So the collision can be contained within the domain here, and that's why you call this collision domain. So you see 1 collision domain for a single network here, 4 collision domains for a single network here. Which one is better?
Bridge network.
Bridge network, right? So you want to divide a single network into multiple segments using this filtering device that does selective forwarding. And in that case, you are dividing a single network into multiple collision domains. How about this? If you can have a bridge that has enough ports where you can connect a single computer one-to-one directly. You have collision domains where only one computer is connected to the collision domain. So, is there a possibility of having a collision in this case? No, there's no other device that you can fight. Even if we want to fight, there's no other computers on your collision domain. So there will be no collision. As long as the switch can handle inbound and outbound traffic as fast as it receives, and there's and that speed is fast enough to avoid the collision. Or switch has a memory where it can put a frame where, for example, if this device, and this device, three devices want to transmit something to this device there, three devices send the transmission at the same time, and there can be possibly a collision because switch has to put 3 frames into a single port, right? 3 frames, 1 line. But if the switch has enough memory, buffer memory for each port, you can put them, the three frames into the memory and send them one by one. And if the speed is fast enough, then switch can avoid the collision, right? And most commercial level switches or bridges have enough memory per port to avoid most of the collisions. So in this case, the collision will be almost 0, and that's how we achieve full duplex switching. That means every device can transmit at the same time when it's receiving signal. You have, yes?
So just to clarify, when you're sending multiple signals to the switch, it's storing them in the RAM inside the switch itself until it's time for that data to transmit?
If there are multiple frames going to the same device, same port, yes.
Correct.
If there's no other frame waiting for or have to handle, then they can be just sent right away.
Okay.
But usually the switches have buffer memories reserved for individual ports. So in case there are multiple surge of frames coming in, then they just put them momentarily and handle them one by one.
Okay.
That's how switches differentiate itself from hubs. Hubs just transmit, broadcast everything to everywhere, but the switches and bridges read the header of the frame where you can find destination MAC address and find out where that MAC address is connected to and regenerate that on that port only. So all the other ports will not hear that frame. They will just stay quiet. So as the switch handle that, process that part, the frames should be stored somewhere. So usually switches have enough buffer memories to avoid collisions and keep them in the memory as it processes. So yes, and if we pay more, so you may wonder why you pay thousands of dollars for a switch. You have a switch plus Wi-Fi plus router in a single small package at home, right? How much do you pay? A few $100, $200? The switches that we have downstairs cost like, I don't know, these days must be cheap now, but when you first got one of the individual switch cost like $4,500. Why? Well, of course they are more reliable, they don't break easily, but also they have enough CPU power and memory to handle large volume of traffic, so they can minimize the collision. So if you can avoid collision completely, and you have a pair of communication channel, one for reception, one for transmission, you can keep listen as you keep talk, right? So that's full duplex. Whereas if you share a single section of the medium, you have to listen, and only when there's no one transmitting, you can transmit, right? So if you use this configuration, star topology where individual device, individual node is connected to individual port of bridge device or switch device, you can implement full duplex switching. Okay? If you can receive signals at 10, or let's say 1 gigabit per second speed, and you can transmit things at 1 gigabit per second speed, but you have to share the medium with others, then on average, your transmission speed will be what? About half of it. If only there are a couple of devices. If you have more device, then maybe 1/3, 1/4 of the maximum speed. If you have only yourself, then you can fully utilize one channel for transmission, one channel for reception. So 1 gig for incoming, 1 gig for outgoing. So the maximum data transmission rate can be 2 gig, where 1 gig is for transmission, 1 gig is reception. And remember, CSMA CD is the mechanism that we use for Ethernet. But if you have that one-to-one connection using Datalink layer device, switches and and bridges, then it still use CSMA CD, but there will be no collision. So what's the reason that we don't use this kind of device instead of hubs? Hubs are in physical layer. They broadcast everything to every port whenever it receives any frame. Is there any reason that we should not use bridges or switches? Cost. Well, if there's complexity, that will be reflected to the cost, right? So cost is the biggest problem. And do we still have that concern? No, because literally no one makes a hub anymore. The memory and CPU became so cheap, now everyone uses layer 2 device instead of layer 1 device. So basically, if you see a box with a bunch of ports, they are all switches, at least 2-layer devices. Then where are the hubs? Museum, maybe? So, in the olden days, you could choose either smart switches, layer 2 switches, or dumb hubs. But from the gigabit, up to the gigabit Ethernet. But if you have 10 gigabit Ethernet, this is a requirement. You must use layer 2 device. You cannot choose to use all the hub. You cannot choose to connect multiple devices to the, you cannot choose to make your device to share a single medium, no matter what you want to use. That's illegal. You will fail to communicate in 10 gigabit Ethernet environment. One channel for transmission, one channel for reception, and usually you have fiber, so 2 threads, one for transmission, one for reception. When you connect devices to switches, you want to choose one of these. This will not happen these days. Even if you want to connect 2 devices, you will still have a switch because it's so cheap. In olden days, like 30 years ago, have you heard the term LAN party? When do you do that? You play a game, right? So there's a great software that allows you to play a game with your friend. But that may be not new to you, but in the olden days, games you just play by yourself. But there was a game that you can connect other devices, but hubs were still expensive, so you just bring your big desktop, 20 kilogram or whatever, hold it and bring it to your friend's house and connect your computer to your friend's computer 1-to-1 directly with crossover cable. Okay? That's how you have this point-to-point connection. Not anymore. You have this for single network, but if you have big networks, a big campus to connect, you may want to have 2 separate switches, one for this wing and another for another wing. So in this case, we have 4 different wings, so you may decide to use 4 different switches to connect computers within that wing. And then you have to interconnect those switches together. Now you have to ask, what kind of communication patterns do you need? Are those traffic usually for internal use? So if your pattern, network usage pattern is most of the users access the database within your network, within your company network, and rarely use the internet, like a bank network. They don't allow everyone to access the internet. There are some computers that are allowed to access the internet directly, but mostly, not mostly, but many of them are in the closed network where you have some servers and desktops interconnected. Not many frames will have to go outside. But if these are a bunch of end user devices and these are servers, file servers, database servers, the traffic will be a lot between these two switches instead of within the single switch, right? End user device, terminal to terminal, there will be not many communication instances, right? Mostly, all these will send something to here, and big chunk of data will come back to this switch. So this is where the bottleneck will occur. In that case, you want to find a switch that supports two different speeds. So, for example, downstairs we have two VSP router switches that has 48 copper connections and two fiber connections. So we can have two 10 gigabit connections, and we actually do have that fiber optic connection between two VSP switches, one for the left half, one for right half of the lab. There's a 10 gigabit connection between the switches, and from the switch to all the computers on the left half and the other switch to the right half are using 1 gigabit connections. So even if there's a lot of communication between the two switches, they can still be supported without too much bottleneck. If you have external connection, then you may consider how much of bandwidth you will need for this and that one. So most of these, if they usually connect something on the internet, this path should be large enough to support that frequent traffic to the internet. This depends on how much of connection or data you need to transmit between two switches. If these guys don't talk to these guys a lot, then this can be the same bandwidth as these individual connections. But if there's a data center with file servers and everything, then you may want to have a bigger enough capacity to support that communication. Another thing to be worried about is when you are using switches, switches are smart, but not so smart. So it is smart enough to make a mistake. Okay? What mistake? Looping mistake. So there can be loop between multiple switches, right? So if we send something here, that frame can be passed back to this and then back to here. So that's a loop. And when there can be a loop, switches without special function called spanning tree protocol can misunderstand the connections or surrounding environment and infinitely duplicate its own frame. We'll talk about that in a few slides, but that happens very often if you don't have the spanning tree protocol enabled. The commercial level switches usually have the capacity, but many of them are turned off by default. So if you create that loop to provide more reliable networking, you actually jeopardize the network and no one can talk. What happens? Because every switch will duplicate every frame that it receives, the whole bandwidth will be filled with the garbage duplicate. And because it creates so many frames again and again and again, it overheats. So if you put your hand on the switch, you can actually feel the heat really gets hot. Okay? I know that because I made a mistake. And I was lucky enough to put my hand on it. It was right next to me. I was just experimenting something in the lab, and I just took some cables off and replugged it, and by mistake, I plugged one cable out of another switch and back to the another, which was already connected to another port. And as soon as I do that, in less than a second, my network was dead. Nothing could actually be delivered. And I was wondering, what did I just do? And when I was standing like this, my hand was on the switch, and I was like, what's going on? Oh, it's hard. So it was that fast to just exhaust this CPU cycle and memory, and nothing can talk. By the way, that $4,500 switch has multiple spanning tree protocols capability, but I just turned that off for that particular port. So that's one thing that you have to be very, very careful.
So you can turn it off and on for each port?
Yes. Well, if you paid enough, yes, it's very flexible. When you pay like $4,000 for a single box, then you should expect that kind of flexibility. It's fully programmable. We have to stop here. For your home switch and access point, probably you won't have spanning tree protocol there. So don't, even if you have extra switch, don't plug them together. Just, you may think, hey, redundancy is good. If one goes down, the other one will kick in and load balance or back up. No, as soon as you plug them in and create a loop, they will just stop the whole network. Any questions so far? All right. So don't forget to at least try a few times the new quizzes and ask a question on the discussion board or send